Okay, so in the last class I briefly explained you how to get two dimensional binary phase diagrams at a constant pressure 1 atmospheric. Then I discussed with you how to apply phase rule in both the single phase regions liquid and alpha, where alpha is a liquid solid phase and L transform the liquid. Now let us do this again once more so that you do not forget. So let us consider first a composition axis, composition x b alpha and I just can have different temperatures that in each dot corresponding to one temperature you can see, and I will be remaining within the alpha phase field. So that means if I select a composition first and then I have many temperatures, still I will remain in the alpha phase field, I do not change. Similarly, if I take a temperature, different temperature, one temperature suppose T1, I can have many compositions where alpha is stable. That means within the alpha phase I can vary both temperature composition alternatively or together. You can have temperature T1, T2 composition, this, so many compositions, still you will be in alpha phase field. So you have two, basically you have two independent variables or two variables rather can be changed simultaneously, keeping in mind that alpha phase field remain alpha phase field, we do not change. So let us do that for the two phase region. As you know, f the degrees of freedom is given as c minus p plus 1. C is the component, p is the number of phase and 1 corresponding to temperature. So how many components here? 2, because of binary phase diagram. So in a two phase region alpha plus liquid you have two phases, p is equal to 2, f is equal to 2 minus 2 plus 1, that is equal to 1. So that means I have only 1 degrees of freedom. In the liquid or in the alpha phase field I have 2 degrees of freedom, but within the two phase field region I have only 1 degree of freedom. What is the meaning of that? Let us first consider temperature. Suppose I have the power to choose the temperature. So I choose the temperature like this. If I choose the temperature, that means I draw a horizontal line with respect to the x axis. And these lines actually are known as tie lines. Please remember this. Although I will be telling many things, but you should remember these are called tie lines. That means tie lines are lines which are drawn parallel to the x axis or parallel to the compositional axis, passing through the two phase region. Why they are called tie line? TIE means tying a knot, right? In a tie you use tie is nothing but something we have to wear or put a knot on tie, that means you tie with it something. So it ties the liquid dust and the solid dust, as you see here. I drawn the 2 points here to this, these are liquid dust and solid dust curves intersected by this line. So that means this line ties two curves, liquid dust and solid dust. Okay, now let us get back. So if I choose a temperature as any temperature, let us suppose here temperature is T0, okay, and draw a horizontal line. Immediately my compositions are of solid is given by this point, composition of liquid is given by this point. This is also very important, you must remember. So wherever the tie line intersect the solid dust and liquid dust, and if I draw vertical normal to the compositional axis, I will come to know the composition of solid and liquid phases. So that means if I choose temperature, compositions of solid and liquid phases are fixed, I can't change. Suppose if I take take a composition, if I take a composition like this is my independent variable, I choose, I have power to choose composition, I choose. So now if I choose the composition of liquid dust, composition of this alloy, then immediately temperatures are fixed. Why? Because this composition will melt at temperature T0, okay, very easily. It will start melting at this temperature, suppose T dash, and it ends melting at T0 because that is the liquid, this is solid dash. Below solid dash everything is solid, above liquid dash everything is liquid. So, in between only the solid and liquid region is present. So, that means if I choose composition or temperature, one of these two other variable is fixed. I can't do anything, I cannot change. That is why I have 1 degree of freedom. I can only choose temperature or composition. So, I hope you understood how to apply phase rule in a binary phase diagram. In a single component phase diagram, application of phase rule is very simple. I have shown you for water, but in a binary system it is not so simple. You have to apply your logic to do that. So, let us now talk little bit about tie lines more. Okay. So, let us discuss about this one more. I go back to one slide and discuss. So, as you see here, I have both solid and liquid in the region, and now I have, when I have two phase region bounded by these two solidus and liquidus curves, which I have told you, obviously if I am engineer, I must know how to measure what is the amount of alpha, what is the amount of liquid present for any particular alloy composition, because it is a two phase, the two phases are present, liquid plus alpha. So, I must be having an idea what is the percentage of the two phases consisting of alpha and how much percentage is due to liquid. Let us do that for a particular alloy composition, and from there actually we will come to know how to apply lever rule, very important concept because I have done phase rule, now I have to do lever rule also. The lever rule is very important for binary quaternary alloys. This rule allows you to calculate the amount of phases present in terms of volume percentage or in terms of other percentage, you can do that. Okay, now how to do that? Let us take an alloy composition XB. This is given by this dotted line. Okay, and so this vertical line is passing through, and let us suppose a temperature T1. There are many temperatures. Okay, see, you can have many temperatures between these two, where solid and liquid coexist. Above this temperature, suppose T2, everything is liquid. Below this temperature T3, everything is solid. So, only between T2 and T3 it is solid plus liquid, alpha plus liquid. So, I have chosen one temperature T1 which lies between T2 and T3 and draw a tie line. Tie line knows what? I told you tie line connects alpha and liquid, tie lines connect solidus and liquidus. That is what I mark alpha, solidus, liquidus, L by these 2 points. Okay. So, now if I see this tie line which intersects the solidus at point A, at point not A, let us use some other symbol. Let us suppose I use a symbol C, capital C, and this is at point capital D. Okay. Forget about that L. So, C and D is my line, which are these, and C and D are the 2 points where this line intersect solidus and liquidus. In between I have marked a point X. Why? Because X is the alloy composition, that XB is the alloy composition. So, therefore, this is XB. Okay. So, now lever rule says very simply the volume fraction of or volume percentage of alpha will be given by this on XD divided by the total lever CD. Well, let me put it in this way. We can always use CD as a lever and XP is the fulcrum of the lever. Okay. All of you have used these hand pumps. So, in hand pumps we use a lever to push the lever to get water out. So, there also the lever has a fulcrum. Similar, same thing, same way, let us assume CD is a lever, LEVER lever, with the XP is the at fulcrum. XB means this point is at the fulcrum. Then volume fraction of alpha is given by XD divided by CD. So, volume percentage of alpha is given by XBD divided by CD into 100, because it is a percentage, that is why. Similar, so that means if you are sitting if alpha is lying on your left, the for volume fraction measurements you have to consider the arm on the right of the fulcrum, on the right of the fulcrum, not on the left. But for the liquid it is obviously same way, it is equal to xp is C or Cxp divided by Cd into 100%. Why it is so? Because liquid is on the right side of myself, okay, for me it is on the right side. So I take the arm on the left side, the Cxp is on the left side. So if you are, that means you take the opposite arm. If you are sitting, if your page is on the right side, you have to take the arm on the left side of the fulcrum. If your page is on the left side, you have to take the arm on the right side of the fulcrum. And this is known as lever rule. This can be easily determined by using mass balance, very simple. And one can actually do different kinds of calculations using this rule. Okay. So I will not go into details of that derivation, but this is nothing but a mass balance, concept. It is not named by anybody else, it is known by the lever itself. So as you see, as C and D is the lever, xp is the fulcrum, then you can do all calculations as I do this. So you can have at any other temperature, suppose I have a temperature T4 where I know the cutting points, okay, its cutting points are EF suppose, and xp is my fulcrum. So you can see here that volume fraction of solid will be alpha will be xbf divided by CEF, okay, here xbf divided by EF. So now liquid is EXP divided by EF. So one thing you can see that as you go down the temperature, the volume fraction of solid is going to increase. That is obvious, more and more solid will solidify as you decrease the temperature. I hope this is clear to you now. So we can move to the next thing, next step. Okay. So before I do that, let me just explain you that there are different types of solution exist, like water with salt, water with sugar. So if you take a water with salt, it will be salty. Similarly, water with sugar, it will be sweet. Okay, but what is atomistically solution means? Solution means the one I have shown you. Suppose in a solution you have solvent and solute, right? So water and suppose sugar, water is solvent and sugar is solute. Similarly, solution is the same concept, but it is in solid state instead of a liquid, because we are all used to liquid. So that is why we always say water and sugar, water and your salt, but the concepts are exactly same. If you understand the liquid solutions, you can understand solid solution also. Atomistically, what is it? Suppose if I take your green atoms as a solvent, and initially suppose I have my solid is consisting of only green atoms, that means only one component. Now if I add another component to it as a solute, like if I add suppose this blue atom or blue symbol atom into it, what it will do? This atom will go and replace the solvent atoms. That is what is shown here. You can see here, these are the solute atoms which has occupied their place by replacing the solvent atoms. Such a kind of solution is known as substitutional solutions. Substitutional means I am substituting one atom of solvent with a solute. That is why it is known as substitutional solutions. Iron with manganese is a substitutional solution. Aluminum with nickel is a substitutional solution. You can clearly understand, to have a substitutional solution you need atomic sizes of similar. You cannot have large difference of atomic sizes. Then one atom cannot replace other, because atom sits in the lattice. So it has specific size. So if I want to replace aluminum atom with a nickel, and if the atomic sizes are very widely different, they will not mix each other. Okay. So that means there is some rule, actually I will talk about after some time, Hume-Rothery rule, where how much is this size difference can be allowed to form such these isomorphous type of phase diagrams will be discussed. Now there is another types of solutions which can happen. Okay, let me explain here. This copper zinc, see here, this is the 3-dimensional copper zinc substitutional solution known as brass. Brass you all know, brass is used in utensil, in cooking utensils or even temples also. So you can see here the zinc atoms which are actually shown as a grey atoms are actually replacing the copper atoms in FCC copper lattice. Okay, that is how this is called substitutional solutions. Now on the other hand, we can also have what is known as interstitial solutions. What is that? We know that if I go back one step further, we know that these are voids in a lattice, nothing is present in this between these points. Now if I have a small size atom and I allow that atom to occupy this small size space, then I form what is known as substitutional solution, and that is what is shown in the 3-dimensional diagram. This is the BCC iron, alpha iron, and there are voids in that. You see carbon atoms are going to the voids. Our steel is like that. Steel is nothing but a substitutional solution of carbon in iron. I add small amount of carbon or 0.3, 0.4 weight percentage, and these carbon atoms then go and sit in the interstitial positions. And as you know, there are different type of interstitials. One is tetrahedral, another is octahedral. These are basically voids. So in it you can actually generate this kind of voids. Let us assume iron only first. This is BCC iron. You can see the unit cell of BCC iron. There is a central atom and there are 8 corner atoms. So you can clearly see if I have 2 unit cell, I can generate octahedral voids. Why it is called octahedral voids? Because if I join these atoms, I form an octahedron. Octahedron has 8 faces. You can see here 8 faces. 1, 2, 3, 4. Bottom one also 8 faces. Basically it has a 4 plus 4, 8 faces. Top 4, bottom 4. So at the center of that there is a void, and in fact for BCC iron the void sits on the top plane, this plane, on this plane. Okay. So there are many such octahedral voids. Similarly there is octahedral voids, similarly there are tetrahedral voids. How do you know tetrahedral voids? Very simple. If I have I can generate tetrahedral octahedral voids many ways, but one of these is that there has to be tetrahedron. Okay. So when a FCC unit cell, this is very easy to show. So this is the FCC unit cell, suppose gamma iron. You can clearly see I can actually have this tetrahedron like this. This is a tetrahedron. Why it is tetrahedron? Because this is 4 faces. So at the center of this tetrahedron I can put a void, I can put an atom, because it has a void. So this is known as tetrahedral void. Okay. Similarly in FCC unit cell at the center there is octahedral void. See, I have drawn the octahedral voids. So carbon atoms actually goes into these voids. They sit there, and that is why this is known as interstitial solution. Steel is known as interstitial solution. Whether carbon atom goes to the voids of BCC or FCC does not matter, but because of size differences it has to go to voids. Carbons are very small, and this is why the steel is so strong, and you will come to know much more as I go along why steel is strong, because carbon atoms actually resist the motion of dislocations to this lattice. That is why steel is very strong, and steel is a wonderful material. It has all properties, but it is a substitution, it is an interstitial solutions. So you understood that solutions can be of 2 types. One is known as substitutional solutions, other is known as interstitial solution. In substitutional solutions, one atom replaces the other atom, solute atom replaces the solvent atoms and forms the solutions, but in interstitial solutions solute atoms goes to the voids, tetrahedral or octahedral voids. This is also very important concept. If you do not understand this very carefully now, there will be lot of problems as I discuss other phase diagrams. So be careful about it. Okay. Now, so we have done all the backgrounds. Now whatever time I have in this class, I am going to discuss a very detailed manner a phase diagrams which is known as copper and nickel. Copper and nickel. Why copper and nickel? Because copper and nickel both have phase center cubic structures. Atomic sizes are similar. Copper has lattice parameter of 3.61 Armstrong, nickel has lattice parameter of 3.58 Armstrong. So therefore, they have similar crystal structures, similar lattice parameters, similar atomic sizes, they will form solid solutions. Now again this phase diagram looks same as I told you, the length separate diagrams, liquid solid phases are separated by length separate region between solid and liquid. So the upper curve is known as liquidus, lower one is known as solidus. There are two phase regions, liquid plus alpha, and three phase fields, there is no three phase field here, and there are basically two phases liquid and alpha, and three phase fields liquid, alpha and liquid plus alpha. You see here the composition between the weight percent of nickel 0 to 100%. Similarly copper also. Copper melts at 1084 degrees Celsius temperature, nickel melts at 1453 degrees Celsius temperature. So that is how the phase diagram will look like. So now if I apply lever rule, okay, let us do that. I described it. Suppose I have an alloy which contains 35 weight percent of nickel, and I want to apply lever rule at a temperature Tb, it is between 1200 and 1300, let us suppose at 1250, Tb is equal to 1250. So what do? I draw a horizontal line which is known as tie line, which connects the liquidus and solidus, okay, and it intersects liquid and solidus at these points. So I draw vertical lines from these points and get the solid composition is 32% nickel, liquid composition is 43% nickel. So as you see here at Tb, solid composition is 32% nickel, liquid composition is 43% nickel. Okay, sorry, this other way, solid composition is 43% nickel, liquid composition is 32% nickel, because the top one is liquidus, bottom one is solidus. So now how do I calculate? That is what is done. The weight percentage of liquid is given by S. S is this arm, this is liquid side, so I go to the opposite arm, S is this arm divided by R plus S. R is the distance between the composition and the liquid composition, alloy composition. S is alloy composition and the solid composition. So liquid percentage is the opposite arm, that is S divided by R plus S, and if you do that, that is 43 minus the 35 is this arm divided by 43 minus 32, so that is give you 73 weight percentage. Similarly, volume weight percentage of the liquid is solid alpha is this side, R divided by R plus S. We go to the opposite arm, R divided by R plus S, so that is equal to R divided by R is basically 32 minus 35 minus 32 is 3 divided by 43 minus 32, that is 9, 3 by 9 is nothing but 27%. So this is the way actually lever rule can be applied. I will solve some other problems later on and tell you how to do that.